Earlier we talked about how double displacement reactions need to be forming a solid, a liquid, and or a gas in the products. Otherwise, if you have aqueous here and aqueous there, you didn't really make anything, you just had an ion soup. The one last topic we hadn't talked about between the solid, liquid, and gases yet is the gases. So we're going to do gas formation reactions here. So you just look for any gas in the products, carbon dioxide, sulfur dioxide, hydrogen gas maybe. At the Chem 101 level, the one I usually emphasize the most is carbon dioxide formation. That would come from having, typically you'll have an acid, and then CD will be a carbonate, or bicarbonate. Salt of some kind. The most famous being sodium bicarbonate. AKA baking soda. So basically today we are doing the baking soda and vinegar sort of reaction on paper. All right, so let's do that. I have two examples today, but the first one will be the vinegar and baking soda reaction. Acetic acid at a 5% concentration is known as vinegar. All right, acetic acid means the acid of acetate. Right, acetate is that polyatomic ion everyone seems to love to hate. I think it's worth drawing at least once in your life, just so that you know what it looks like. All right, so there's acetic acid, vinegar. So we would write this chemical formula out as C2H3O2. And hopefully now I'm helping solve the mystery of why acetate is given this long and crazy formula of C2H3O2 minus, and that's because we are referring to this part of the molecule right here. All right, whereas the H plus part is right here. Okay, and so when vinegar is acting as an acid, this H plus right here might react. So this might bump off by these electrons being transferred to the oxygen. That hydrogen bumps off, and it becomes an H plus to be absorbed by the water in the solution or by some other molecule it's reacting with. But it's a H plus, and because electrons are transferred here, we end up with a minus here on the acetate part. So that's kind of what's going on behind the scenes in an acetate acetic acid molecule. All right, it's not like vinegar dissociates a ton in water. It does dissociate a little bit though, so it's a weak acid. But that's a topic for a different video. I just wanted to show you what acetic acid actually looks like in a chemical structure. So the long story short, yeah, you're stuck writing acetic acid this way, or some instructors will have you write it that way, or some will have you write it that way. If you're wondering why two O's in a row, well, that oxygen has a double bond, whereas that one has a single bond. But we'll stick with this here. All right, hopefully I helped explain and demystify acetate. One thing that helps me is there's a 2, 3, 2, 1 pattern between the atoms and then the 1 minus charge. 2, 3, 2, 1. So I kind of envision a pyramid in my head. It goes 2, 3, 2, 1 in my head. All right, and then we have sodium bicarbonate in the kitchen. This is baking soda. Sodium plus bicarbonate is HCO3 minus. If you have trouble with bicarbonate, bi means we added H plus to the chemical formula. So maybe you know what carbonate is. It's CO3 2 minus. Bicarbonate forms when it's reacted with one proton from an acid, and because it has a plus charge, it's going to neutralize one of the minuses, which gives you this bicarbonate. So, man, I must have talked for like 3 or 4 minutes already without having done the problem yet. Anywho, so now that we know the chemical formulas, we can begin trying to do a double displacement reaction. So let's write out this chemical formulas again. HC2H3O2, aqueous, and then we have NaHCO3 aqueous. All right, so this is going to be double displacement. We have two compounds that have a plus side and a minus side. And so it's time to do the double displacement on paper. So here is what I'm doing here is I'm just making sure that you can see the different ions going on. Some students maybe struggle with that if they haven't mastered their polyatomic ions yet. You need like 100% mastery of all polyatomic ions to do these equations. I think the answer is probably no, but I think getting to a decent level of comfort is pretty important. So let's write out these ions so we can charge balance them. All right, so I'm going to add enough H plus to HCO3 minus until it's neutral. That's going to give me a total of 2 H's. So rather than writing HCO3, we will write this as H2CO3. All right, so that's our first, and then we will form our second. All right, and this is sodium acetate. So we made carbonic acid and then sodium acetate. So let's write those products in. I'm going to move myself over there. So our first product was H2CO3, and then so that's carbonic acid, and then we have sodium acetate. Everything was a +1, -1. They're all the same number for the charge number, which means this equation auto balances. All right, it's nice when that happens, so I made sure my next example would not be as nice. All right, so now let me pause here. Perhaps you're noticing on paper, everything is aqueous on both sides. So Josh, didn't you just make an ion soup? We have no reaction, right? I can't wait to just write no reaction, because that means I can get full credit without thinking about the problem anymore. Except, let's think about experience. Experience is when you mix vinegar or baking soda, you get bubbles. But we don't see any bubbles here. So, when it comes to reactions with carbonates or bicarbonates, and here we have a bicarbonate there, in acid-base reactions involving the weak base of carbonates or bicarbonates, you are going to form carbonic acid. Okay, so let's write that down. Okay, acid-base reactions with CO3 2 minus or HCO3 minus carbonates or bicarbonates form H2CO3 aqueous. Okay. But this is not what we see. We see bubbles. All right, so this is the interesting tidbit for today. Carbonic acid is not a stable acid in water unless it's kept sealed and maybe pressurized. Container will help a little bit, aka a soda can. All right, this is how carbon dioxide is stored in a sparkly beverage. All right, what they do is they take carbon dioxide gas and dissolve it into the water, and in the process of dissolving in the water, it's going to react with a water molecule and form carbonic acid. All right, this is done under pressure at the canning or bottling facility, and then it's sealed so it stays this way and doesn't undo itself. Once you open the bottle or the can, then the reverse starts happening, where your carbonic acid is degrading into carbon dioxide and water. But when you open the bottle or the can and you start drinking, the reason why it stings your tongue a little bit, or at least part of the reason, is you have a lower pH as a result of this acid being in solution. So I guess one thing you could try if you're into experimentation is rate the acidity of a drink when it's freshly opened versus when the soda has gone flat. But this is the reaction you need to know. All right, this is the main focus of this video, is acid-base reactions with carbonates and bicarbonates. You're going to make carbon dioxide gas. That means that this is not the final way we write this reaction. We are going to substitute these two values like a mathematical equation, since that is like equal in quotes to that, we can apply a substitution there. All right. So you can just substitute immediately, or and then rewrite it, or you can do like a systems of equations sort of approach. So that's what I'm going to show here. I'm going to show like a series of equations. Right, so we had for the first reaction, all right, I'm just rewriting. By the way, this last chemical called sodium acetate, this is how you season salt and vinegar chips. Because vinegar itself will evaporate, it's wet, you can't put it, onto chips, except maybe if you're like serving it really fresh. This is like a solid state version of vinegar, okay? It also provides some saltiness with the sodium as well. All right, so yeah, we basically learned how to make the salt and vinegar seasoning at home. You could do this at home to make your own salt and vinegar seasoning. All right, so the second equation is going to be the decomposition of carbonic acid. Degrades into a water molecule, which is a liquid, and then carbon dioxide gas, which leaves the system. So for gases, I like to write up arrows on them. All right, so they're asking you the answer for this reaction, acetic acid plus sodium bicarbonate. I feel the best way to answer the question would be with providing two reactions this way. as your complete answer. If you were asked for an overall equation, then they would want the intermediate of carbonic acid removed. Okay, so just like an equal sign, you can cancel a term if you have the same number of it on both sides. We have one carbonic acid here, one carbonic acid there. If they don't want any intermediates, then the carbonic acid would not appear in the overall equation. So we would just take everything on the left with all the equations and everything on the right, and then we would write our overall equation, overall reaction. All right, so I go through like a Sharpie a day, it seems like. I'm gonna press hard, get everything I can out of this one before getting a new one. All right, so all right, and that would be the overall reaction. Okay, vinegar, baking soda, water, carbon dioxide, sodium, acetate, salt, and vinegar seasoning for chips. All right, that was the first example. Let's do a second example. All right, we're gonna do something similar, but let's work with a carbonate instead of a bicarbonate. All right, so hydrochloric acid, HCl aqueous, and then potassium carbonate, and I intended to write AQ there, so we're going to go K2CO3 aqueous. All right, so let's react those two together. All right, time to figure out the products. We're still going to make carbonic acid. We're going to end up needing 2 of these to charge balance the carbonate, H2CO3. And then KCl, potassium chloride, salt substitute. All right, now that we got the products, we can drop them into the equation. And we can start charge balancing. All right. Now, I do remember that H2CO3 carbonic acid will degrade into a CO2 and H2O. You could substitute that in immediately if you like. In my opinion, I think it's actually easier to balance the equation first and then apply the substitution later. So I'll try to show why I think that way. All right, so hearing from you all, you like it when I balance equations on the fly better so far. If you like it when I do the middle way, that's fine too. I had a student share with me that they were scared that doing it, showing what's going on the left and right is like required. No, that's not required. At least I don't require that. All right, so most complicated looking formula to me is the H2CO3. So we'll try to get that nice and balanced. All right, so 2 H's on the right means 2 H's on the left. And 1 carbonate already on each side. Since I created 2 chlorides, I should clean that up by putting a 2 here, and then I'm just going to hope that I have 2 potassiums on the left side, and I do. So now this equation is balanced. All right, now that I've balanced the equation, I can now do the work of applying a substitution of this reaction for that. Okay. And let's write that overall reaction answer. Water, carbon dioxide, and don't forget the 2 potassium chloride formula units. All right, so that's how you do double displacement acid base with carbonates and bicarbonates forming carbon dioxide gas. All right, hope this helps, and I'm happy to take any questions or comments. Thank you. Take care.